Now that we've written out what we know, we're going to move to step 4 now, which is to write an equation that relates the variables, hence the lesson related rates. Now you can't really have a rate until you take the derivative. However, we want to relate all the variables that we wrote out in steps 2 and 3. We take a look at this first example of water pouring into our tank. What variables do we have? Well, we have the length of the tank, we have the width, height, and we have the volume. So what you need to do is basically take all those variables and think about how they relate to each other. Hopefully you paid attention to geometry and know different formulas for volume and surface area and things like that. Reason we did step 1 or example 1 like this is because it's a pretty simple formula. So the question is, how do you relate length, width, height, and volume? And the answer is the volume of a rectangular prism or a box, which is V equals LWH. Now, or length times width times height. Now, in this particular case, we said that the length and width was constant. Okay, so we can actually go ahead and just plug those straight into 3 for length and 2 for width and get V equals 6H. Okay, and I will tell you right off the bat, you usually want a formula in terms of 2 variables. Okay, you'll see why that is later. That's not always necessary, especially if you're given 2 rates or something like that. But this is what you want. If you have a an equation with 2 variables, you should be good to go. It's going to make it a lot easier. So in this case, we just have the volume equals 6H. In terms of this, conceptually, in terms of the picture, basically, whatever the height is, okay, let's just say the height is 1, volume would be 6 times that, the volume of the water. So if the water was 1 meter high, the volume would be 6 times 1, 6 cubic meters. Okay, so that's pretty much it for step 4 for example 1. Want to again write an equation that relates all of the variables and simplify that down as much as you can. The only reason again we're able to plug in 3 for L and 2 for W is because those are constant. They don't change, okay? The length and the width of the water in this tank will not change. Now if it was a cone, we could not do that because it does change. All right? So that's our formula for example 1 for step 4. Let's go ahead and look at example 2 and see what we're going to write for step 4 for it. So here we had the ladder sliding down the wall. We want to be able to write an equation that relates all of our variables. Okay, so we have the height of the ladder. It looks like we have the distance the ladder is away from the wall. We have the length of the ladder. Now if you draw a picture, this is another reason why we want to draw a picture, be able to see which kind of shape you're dealing with. Now we do have a triangle, but it's changing, right? And so unlike last example where the length and the width of the tank was the same, the height that this ladder is from the ground is going to be changing as it falls, same as the distance it is away from the wall. So we will have a formula for a triangle. Now how do you relate all of these things? Well, notice it's important here, this is a right triangle. So does anybody remember the theorem that relates all 3 sides of a right triangle? If you said Pythagorean theorem, you are correct. Okay, so again, just to review for step 2, here's all of the variables we had for the height, and x being the distance from the bottom of the ladder to the wall. And then L, of course, is constant, 5. So if we relate XL and 5, which is the length of the ladder, it'd be x squared plus h squared equals L squared. Again, the length of the ladder does not change, so you can go ahead and plug in 5 to get 5 squared, which is 25. So here's our formula, x squared plus h squared equals 25. This will complete step 4 for example 2, which is to write an equation that relates all the variables. And again, when you see that you only have 2 variables in the equation, that's good. That's what you want. All right. You're good to go at that point as long as you just follow through with the rest of the steps. It makes it a lot easier if your equation is in terms of 2 variables. So for example 2, we have x squared plus h squared equals 25. All right, so let's go ahead and take a look at example 3. We had the water pouring into the cone. Here's the wording of the problem, coming in at 6 cubic meters per minute. Here are our variables. We have an H, we have an R, and we have a V. Now you might be thinking, well, how come you're ignoring these rates? Well, that will come into play when we take the derivative of our formula, okay? So, you have like an original formula, which might include volume or surface area, or in the last case, the triangle and the right triangle side lengths. These will come into play once we take the derivative of that formula. So you just want to look at the regular measurements, H, R, and V. And I've already alluded to this, since it's dealing with the volume of a cone, and we know H and R, or we can figure out H and R, whatever the case, we will use the volume of a cone, which is 1/3 pi r squared h. Okay? The question now is there anything we can plug in? Well, let's see what we wrote. Okay? We wrote that the height is 5 meters of the water. Okay? So the question is, can you plug in 5 for h? The answer is actually no, because h is not a constant, okay? The water level is going to continue to rise here, okay? And so, at this particular point in time, it's 5, but not always 5, right? For example, when the cone fills up, the height of the water will be 10 meters. So you can only plug in a number into the original when that number is constant. And even the radius here is going to change as well. Of course, we don't know what it is right now, but the radius of this water will change. And so the answer is no, you cannot plug in 5 for h. You won't be able to do that until you take the derivative, which will give you the rate of change. So in this one, we have 3 variables, v, r, and h. There's really nothing we can plug in. We can't plug in v, of course it's changing as well as the water fills up. And so you might think, well, can we solve this if we have 3 variables? And the answer is yes. This is why I saved this for example 3, because it's a little bit more involved, but that's okay. You can solve it with 3 variables. Just be careful that you don't plug in a variable into the original formula, because it changes, right? You can only plug in constants. None of these R, H, or V are constant, so we cannot plug them in. But that's okay. We will be able to solve this, and this completes step 4 for example 3. The last example, we had the coffee draining from a conical filter into a cylindrical coffee pot. And the question is asking how fast is the level in the coffee pot rising? So basically, the rate at which this is going up. This one is way more involved than the first 3 because we have 2 different shapes. For step 3 again, we write out what we knew, which was the height of the cone, the diameter d2 of the cylindrical pot. Now we could also write r2 equals 3, right? That's pretty obvious. That's half of the diameter. We have the rate at which the coffee is dripping out of the conical filter, which is I think it's 1 inch per minute. Is that the units? Yes. But the real question we have now is, what formula are we going to write to relate all the variables? Now, since we're solving for the coffee pot, the level in which this is rising, and this involves the volume of coffee, we just need to write the formula for the volume of a cylinder, which I alluded to before. It's the area of the base, which is a circle, times the height, so pi r squared h. Step 4, we're going to write an equation that relates the variables. V2 equals pi r squared h. Now, since we have 2 different radiuses, one for the cone, the coffee in the cone, and one for the coffee in here, we said that everything here we're going to label R2 and H2 and V2. So it's V2 pi R2 squared H2. Now the thing is, the radius in this will not change, right? radius in this will not change of this water. It will always be 3, half of 6. So we can write V2 equals pi times, whoops, not 6, it's 3. 3 squared times H2. Now the level will rise, right? So we can't plug anything for H. But when we simplify this down, we have V2 equals 9 pi times H2, which represents the height of the coffee in the cylindrical coffee pot. Okay, so that completes step 4 for example 4. This is our equation that relates the variables. And again, we have a formula now that has 2 variables in it. Pi is not a variable, but the height and the volume is the only 2 variables we have in this formula. And again, that's what we want if we can. In example 3, we didn't achieve that, but we can still solve it. That's it for example. Step 4. Again, you're just writing out an equation that relates the variables and trying to simplify it as much as you can. If you have any other questions about this step, let me know.